Hello again. I'm not crying, I swear. I'm recording this video for the third time. Hopefully it works this time. I'm not going to rewrite everything. I've already rewritten it twice. Don't worry. I cleared up space on my iPad, so it should actually record this time. But if I talk a little fast, it's because I hope it's not too long, so it actually saves for once. Okay, AP Physics Virtual Lesson Review. Yay, simple harmonic motion. My goal for the lesson today is so that you guys could get 6, 7, 8, and 9 done without yanking your hair out or making yourself cries and stuff like that. Okay, great. So if you review here, we have position, we have velocity, we have acceleration as a function of time. Position, amplitude times cosine times the angular frequency times the time plus the phase shift. Usually harmonic oscillator will start at maximum displacement, making the cosine function ideal. If that's the case, then the, what do you call this thing? Delta, the phase shift is 0, and the function looks like that. So that's usually the case. In any case, you can, just remember that. The derivative of position is velocity. Derivative of cosine is sine, but it's negative. And of course we have the chain rule, so the omega comes out in front. The derivative of the velocity is the acceleration, and you have the chain rule again, so you get negative a omega squared times the cosine, which as a reminder is acceleration is a negative omega squared times the position. Anyway, that's going to come up later, you'll see. Your relationship between period and frequency, of course, are inverses, as you can see here, but then also your relationship between period and angular frequency is right here. We could also write this as frequency times 2 pi is the angular frequency, but it's all whatever. You guys got that down, hopefully. All right, and then very important for today's lesson, at least for number 6, is the fact that the force is the negative derivative of the potential energy with respect to position. And likewise, the integral of force with respect to position times -1 is equal to the potential energy. So same old stuff there. Oh, great. Okay, so we're going to go ahead and get started with number 6. I swear, the first 2 times I recorded this, it was so much better, guys. You should have heard. You'll never know. Okay, so here's number 6. Now, number 6, boy, what a mess. What we have going on here is a mass spring system. We got this thing oscillating back and forth, and all they do is they give us a potential energy function. They also give you the mass as a 0.5 kilogram, and they tell you that this sucker is oscillating back and forth, and they want to know maximum speed, right? So the maximum speed is going to, well, there's a couple ways to, no, there's really only one way to do this. That's the thing. There's a couple things that might go through your mind, and I'm going to make sure that you guys don't make a mistake and waste time trying to solve this one way as opposed to the other, okay? So in any case, if we look here, with this potential energy function, we can take a derivative of that, and we know we're going to get force if we run a negative sign through our derivative. So that's what you see right here, right? We got our force function, and we have negative 6x minus 8. That's our force because we took the negative derivative of our position, potential energy. With that said, why is that significant? Well, you're supposed to find the maximum velocity, and the maximum velocity is going to happen at some point during this sort of back and forth motion here, right? So when does that happen? Well, I'm not going to tell you, but I'll leave it up to you to think about that. We already know. You should have it in your notes somewhere, but just think about that, right? And full disclosure, you should probably do part B on this problem first. And the reason for that being because your max velocity depends upon you knowing where it's oscillating around. So part B says find the position around which it oscillates, something like that. So you're going to go ahead and do that first. You can do that using what you see right here in front of you. So I'll just leave it at that. Go ahead and find your position about which this thing oscillates. And then the question becomes, okay, so how do I, given what I have here, how do I figure out its maximum speed, okay? So what you see below here is, I'm going to add something to it real quick. You see this potential, or this mechanical energy conservation equation, okay? So they don't say anything about friction, so we should assume mechanical energy is conserved. And with that said, we have kinetic plus potential equals kinetic plus potential, right? Well, this is basically going to be your approach, okay? Once you know the position about which it oscillates, then you can figure out the energies involved. And if you were looking for maximum speed, then obviously kinetic energy is going to come into play here. Now they tell you it starts at 0 and equilibrium, so it starts at rest and equilibrium. No, it starts at a position of 0. I don't know how they worded it. I don't have it in front of me anymore because I'm tired of recording it 11 times. Anyway, the point is that because of that, the kinetic energy is 0 in the beginning. Okay, cool. Also, they tell you that the potential energy, it starts at the origin or equilibrium, whatever it is. The point is, even though it's starting at x equals 0, that doesn't mean your potential energy is a minimum. That's actually a weird thing. Remember, our potential energy 0 point is arbitrary. So even though the potential energy could be 0, that doesn't mean that it can't get lower. Okay, so just keep that in mind. In any case, the bottom line is you'll use this equation right here. You're going to solve for the velocity, and that'll be the velocity that you're looking for, the maximum velocity, which corresponds to the point where the potential energy is the lowest. So I'm talking too much now. Okay, real quick, I just want to mention an approach that you may have thought of or tried that didn't work, and maybe caution you against it. This is an important lesson. If you look at this equation right here, you see mass times acceleration, right? So you could divide by mass, and you could get an acceleration function. So then you have an acceleration function, and you're thinking, hey, if I know acceleration, I can integrate to get velocity. Okay, actually, no, you can't. Why not? Well, the acceleration is the derivative of velocity with respect to time, and velocity is the integral of acceleration with respect to time. But this isn't time. This is position, right? So we have our position function here. And what that means is you cannot integrate the acceleration and get the velocity with respect to position. That is not valid. It is not correct, and you will get the wrong answer. So if you took an approach, or you're planning on taking an approach where you integrate your acceleration to get velocity and then you plug in your position, it's not going to work, because the relationship between acceleration and velocity with respect to position is not an integral. It's more complicated than that. So in short, avoid that approach. Take an energy approach. You're good. Wow, I'm talking too much. Okay, number 7. Number 7, you have this force function given. It's quadratic. Part A wants to know, what's the equilibrium point about which it oscillates, I believe is the way they worded part A there. So yeah, what you're going to do for this problem is, first of all, what does the word equilibrium mean? Well, of course, it means that the force is equal to 0. So if the force is equal to 0, then you can find that position, right? So that's easy, simple quadratic there. So with that said, what does this even say? Jeez, I don't even know. X is ting. I don't even know what that says. So I'm sorry. We're gonna talk about it in a second, but I'll make that a little bit more clear. Anyway, so you find your position, right? So then, I was writing tiny. X. That's what it said. X is tiny. I forgot. There you go. I knew it would come to me. Okay, so for part A, you find your position where f equals 0. You're done. Now then, in part B, it says, hey, okay, so we want you to figure out the period of oscillation, assuming that the amplitude is really small. So x is tiny is what I wrote there. So if the amplitude is really small, then what does that mean about our oscillation, right? Well, it means that if x is tiny, then x squared is going to be uber tiny, right? X squared is going to be vanishingly small, okay? So once we know that x is small, then we understand x squared can be completely ignored. So we're not even going to worry about it. We can ignore it, okay? Now, if that's the case, then you might say, okay, fine. Well, if x squared is gone, then my force function looks like this. We have 5x plus 2. But in reality, that doesn't make sense quite either. Why not? Because if x is 0, then F would be 2. And what that implies is that the spring is applying a force when it's not stretched. Well, springs don't do that, right? So we actually don't want that 2 there either. So the actual model that we're going to use for number 7, as it turns out, when we want to find the period of oscillation, is just F equals 5x. So I'll leave it to you to find the period from that, but do understand that the answer key has an error. It says 3.7. It's actually 3.97. So we missed a 9 there. So in any case, that's number 7. You guys can figure that out. Okay. Yippee skippy here. Let's go ahead and move on to number 8 as I clean things up here. All right, number 8 is misleading, or you could easily take the wrong approach. So I'm going to help you guys out, save you some time here. On number 8, you have this situation where this cart is heading towards a spring, and it compresses the spring, right? So that's what we see right here. This cart right here is compressing that spring and sort of just making that spring go inward. Then the spring is pushing back, so the cart goes flying back to the left. So then the question they want to know is, what is the time for which this cart is in contact with the spring? So you might be tempted to think, okay, well, I know how fast it's moving, so if I know how fast it's moving, then that can help me find kinetic energy. Kinetic energy is going to be equal to potential energy, and then I have like the X you can find from that, and maybe I'll take like a momentum approach or whatever. That's actually, you could probably do it that way, but it's much easier, so let's just save some time here, right? So instead of worrying about this cart compressing that spring and thinking about it from an energy point of view, let's just think about it from an oscillation point of view. And that's why I've drawn what you see right here to draw your attention to a comparison between this happening and the oscillation of this mass on the spring. Now the cart's not attached to the spring, and that's very important because what's going to happen is the cart's going to run into the spring and compress the spring from here to here. The spring's going to push back, and then it's going to go back from here to here, right? When the spring pushes back, the cart is then just going to leave. It's going to get detached from the spring, and it's going to be gone. Now, if we think about how this compares to a mass oscillating, I should have drawn that as a spring, a mass oscillating on a spring, well, what happens? If the mass gets compressed backwards, then it eventually, it eventually then comes back forward and then goes backward and forward again and again and again, right? So that's what's happening there. Now, how does this compare to our picture up top? Well, it's actually similar, but not quite the same, right? We have here, if you look, this is one amplitude, right? And then this is another, and another, and another. So how many amplitudes in a period? Well, we know that there should be 4 amplitudes in a period. And if we look at our situation here, we see there are only 2 amplitudes. So really what we have here is a certain amount of time. And I'm not going to tell you how much because you should be able to figure it out by now, and you should be able to solve for that amount of time, and I'm going to shut up because this is easy. Okay, number 9. Number 9, we have a mess. I'm going to clean this up just a bit. Like I said, I've recorded this video so many times. I'm so tired, guys. I'm so tired. Okay, here we go. With number 9, we have a situation that I'm drawing our attention to. I really want you to focus right here for a minute, okay? We're looking at a mass on the end of a spring. And what I've done to the right here is simply write a Newton's second law equation. If there's a spring pulling on a mass, then the net force is equal to kx, right? So that's very simple. There's a negative sign in there. Don't worry about it for now. With that said, the correspondence, or the that I want to bring your attention to here, is if we divide this equation here, right? If we divide both sides by the mass, we get this equation, which is acceleration equals k over m times x. Now, if that's a maximum x, then we would have a maximum acceleration, and that's what I want to draw your attention to right here. So we now have this situation here. Now, this equation that I just drew an arrow to is actually an equation that we saw at the very beginning when we talked about our acceleration. So here we're back at our acceleration function. Now, if we maximize this, so we have a max, right? Then with a max, we have cosine being 1. So we'll have negative a omega squared times 1, which of course is just negative a omega squared. And that's exactly what I'm doing down here in number 9. We know that we have a situation with a mass on a spring where we have a maximum acceleration. And so, well, I mean, it doesn't matter. We're just examining the idea of a maximum acceleration, right? And with our Newton's second law equation right here and this equation right there, both of which we know are true, we can draw a conclusion, and that is that omega squared is equal to k over m. So this is where we get our equation for the period or the frequency of a mass spring system. It comes from Newton's laws, okay? And so it is this very important correspondence right here between k and m and omega that I want to draw your attention to. So we get this conclusion that omega, which I'm going to fix because it's ugly, omega squared is equal to k over m, and that means omega is equal to root k over m. Now, that is true for this simple system right here, a mass on the end of a spring. Number 9 wants you to do something else. It says, hey, what if you have this situation right here, right? What if you have this wheel that is attached and free to roll on the end of this spring? What's going to happen then? Well, what do, right? Well, we have rolling without slipping, okay? And whenever we have rolling without slipping, then we have a certain process that we go through, and that's the process you should approach here, okay? In other words, I'm going to draw a free body diagram, and I'm going to do a net force equation with F net equals ma right here, and I'm going to do a net torque equation, net torque equals I alpha. If you do that, and you combine your equations, then you should be able to get some sort of expression like this. But instead of seeing the angular frequency as root k over m, you'll find it as something different. Now, of course, you can look at the answer key to see what that is, but the bottom line is you should be able to get that from the fact that you know I is 1/2 mr squared, and you should be able to draw your free body diagram as I've shown here. That'll help you with your net force equation. In any case, you will end up with this, right? You'll end up with an expression, if I could erase, you'll end up with an expression, omega squared, A equals blank times x. You'll have some coefficient here, and that coefficient corresponds to your angular frequency. Once you know your angular frequency, you know you can find your period. So in any case, that's the general approach you're going to take for number 9. Do a net force equation and do a net torque equation. Combine those two. See if you can get yourself an expression for acceleration, and then draw that sort of parallel to find your angular frequency, okay? Oh, boy. This should save, and I sure hope so. So I hope you guys found this useful. These problems are kind of tough, so it's going to take you some time. If we need to correspond with like video conferencing, voice chat, whatever, leave me a comment or send me an email, and we'll make do with whatever we work out. Maybe we could do one-on-one voice call, or we could do like a group Discord, who knows. In any case, hope you guys find this helpful. Do spend some time with these problems. I'm not going to do them for you. I've already kind of like outlined them very well. But if you have individual questions, I'm certainly happy to help. Hope you've enjoyed your long 3-day, 4-day weekend, whatever it was, and we are certainly gonna plow through this uncharted territory together. But I want you guys to know that I'm committed to making sure that you guys continue to learn and continue to understand AP Physics and move through this. So we're all in this together, so I'm gonna certainly do my part. I'll see you guys soon. Bye.